Hey everyone, and welcome. Have you ever thought about whether the path you walk is actually the shortest way to get somewhere? Well, today we're going to unlock a kind of physics superpower that answers that exact question. We're diving deep into two-dimensional motion, and believe it or not, it all kicks off with a simple walk to a friend's house. So imagine this. You walk a total of 14 blocks, following the sidewalks, making all the turns. But what if you could just travel in a perfectly straight line, like a bird flying from your front door right to theirs? Is that as the crow flies path any shorter? Well, the answer to that question unlocks a really fundamental principle of how pretty much everything moves. All right, let's actually map this journey out. Just picture a city grid made up of perfect square blocks. This is our little laboratory for today. Your path isn't just some long, random walk. It's actually made of two very distinct straight line movements. Okay, so first, you step out your door and you head east for 9 solid blocks. This is the first piece of the puzzle, the first component of your motion, just a simple, straight line going horizontally across our city grid. Then, you get to a corner, you make a sharp 90-degree turn, and you start walking north for another 5 blocks. And that's the second piece, the vertical part of your trip. And just like that, you're at your friend's place. So what's the total distance you actually walked? Well, that's easy, right? 9 blocks east plus 5 blocks north. That equals 14 blocks. Your fitness tracker would be very proud. But, and this is a big but, in physics, that's not actually the most important number here. We all kind of know that the shortest path between any 2 points is just a straight line. So how do we figure out that direct, as the crow flies route? Well, to do that, we need to stop thinking like someone stuck on a sidewalk and start thinking like a physicist. Now, the tool we're going to use is called a vector, and don't let that word scare you. A vector is just a fancy way of saying a measurement that has both a size, like how much, and a direction, which way. Your walk wasn't just 9 blocks, it was 9 blocks east. And it wasn't just 5 blocks, it was 5 blocks north. See? Both parts of your journey are vectors. Now, if you look back at our grid, at our little map, what do you see? The path east and the path north, they form 2 sides of a right-angled triangle. And that straight line distance we're looking for, that's the hypotenuse. Which means we can solve this whole thing with an old friend from math class, the Pythagorean Theorem. And the math is actually super straightforward. We take our 2 sides, A and B. So first, we square the 9 blocks east. 9 times 9 is 81. Then we square the 5 blocks north. 5 times 5 is 25. Add those two together, you get 106. And for the final step, we just take the square root of 106. And boom, there's our answer. The straight line path, which physicists have a special name for, displacement, is only about 10.3 blocks. Think about that. You walked 14 blocks, but you only ended up 10.3 blocks from where you started. That's a shortcut of almost 4 blocks, all figured out with a little bit of math. This really highlights a huge difference in physics. Distance is the total ground you covered. It's the 14 blocks, kind of like the odometer in a car. But displacement? That's just the straight line from your start point to your end point, only 10.3 blocks. 2 very different things. But wait a minute, why does this even work? How can we just take this journey, split it into an east part and a north part, and just treat them like a simple triangle? Well, it's all because of a really powerful, fundamental principle of motion. Here's the secret sauce. The horizontal and vertical components of two-dimensional motion are independent of each other. What that really means is that your movement to the east had absolutely 0 effect on your movement to the north. They were like 2 separate events happening at the same time, which is exactly why we can analyze them separately. I know, this idea can feel a little counterintuitive, so let's use a classic thought experiment to really nail it down. Imagine you're standing on top of a really tall building with 2 identical baseballs. You drop one so it falls straight down. At the exact same millisecond, you throw the other one perfectly sideways, horizontally. So, what do you think? Which ball is going to hit the ground first? The one that just fell straight down, or the one that's flying sideways through the air? Your gut might be telling you one thing, but the laws of physics, well, they have a pretty surprising answer. Believe it or not, they hit the ground at the exact same time. Yep, it's true. But why? Because gravity doesn't care about sideways motion. It pulls down on both balls equally. The horizontal motion of that thrown ball is completely independent of its vertical fall. Its sideways speed has literally 0 effect on how quickly gravity pulls it to the ground.
So this isn't just a cool fun fact. This principle, the independence of motion, this is that physics superpower we talked about at the beginning. It's like the master key that lets us unlock and understand almost any complex motion in the entire universe.
All right, so let's do a quick recap. We've learned that any complicated motion can be broken down into simpler, perpendicular parts, like horizontal and vertical. And the crucial thing is, these parts are independent. They don't mess with each other. This lets us turn a messy two-dimensional problem into two simple one-dimensional ones. And of course, now we get the huge difference between total distance and straight-line displacement.
Just think about the beautiful curved arc of a kicked soccer ball. It looks really complex, right? But now you know it's just two simple things happening at once: a constant horizontal motion and a vertical motion totally controlled by gravity. By looking at them separately, we can predict exactly where that ball's going to land. And this same idea helps us figure out how satellites orbit the Earth.
And that leaves us with one final thought. This whole method of breaking down a complicated problem into its smaller, independent pieces, it's one of the most powerful tools in all of science. It works for a simple walk across town, and it works for a satellite zipping through space. So what other complex things in your world could you understand a little bit better by looking for their simple, independent parts?